Okay, hello. So this is a continuation of section 2.6. Oh yeah, so what happened on Wednesday? On Wednesday, I think I had some like vaccine side effects and I got like crazy nauseous, like could not make it through class, even a virtual class. So that's why I recorded later in the night when I felt better. I recorded our what was going to be the material we covered that day. So I got through most of 2.6, and that's what I'm going to finish today. So if you haven't watched if you haven't watched that February 17th meeting video, it's in Canvas under modules. Hopefully you did get to watch it though, because this lecture is going to build on that. So 2.6 continued. Okay, so in this we're talking about shapes of graphs or rather graphs of functions. So we're talking about graphing functions, and the way that we're structuring this is we talked about some base graphs, right? We have base graphs. For polynomials f of x equals x to the n, or power functions. These are called power functions. We have this sort of, let's see, two categories here. And I'm going to go through this real quick because, like I said, I covered a lot of this either on Monday or Wednesday. So this is the shape when we have an even n for this type of power function. And then this is the general shape, the base graph shape, when we have an odd n. Then we had three classes of functions. We had the power functions. We have the root functions. Can I fit this on another? Okay. F of x equals the nth root of x. And those two, so each one of these categories of functions is going to be able to be split into even and odd. For n being even here, for a root function, we have this general shape. For an odd root function, we have this general shape. So that's supposed to go through the origin there. This is for an odd n. Okay, so that's power functions, even odd, root functions, even odd, and then what we called reciprocal functions. Sorry, there we go. Reciprocal functions, which looked like f of x equals 1 over x to the n. We had our even odd versions of those, and these are the ones that had asymptotes, right? Meaning those points where the function starts blowing up to infinity or negative infinity. So for an even n, we had this sort of shape. So this is like, for example, 1 over x squared or 1 over x to the fourth, something like that, where n is even. And there's a lot to say about these because of that asymptote behavior, right? But I'll point that out more as we start scooting these functions around. And then here's a picture of what they look like for an odd exponent n. So this might be 1 over x or 1 over x cubed, something like that, where n is odd. And I go over the construction of these in detail. In fact, I think by Monday we had gotten to these shapes. So then the Wednesday recorded lecture, I go over like in detail the construction of these. And also, we're now going to start moving into, well, actually in Wednesday's lecture, I start moving into transformations of functions. So this is moving into 2.6 territory. All of these base graphs is kind of like 2.2 territory. I want to say one more thing about remembering the shapes of these graphs. Just make some flashcards. You know, that junk works. I mean, I never really was one for studying, especially mathematics, to think of using flashcards, because the moment you tell a mathematician to memorize something, they're gonna be like, no, like I want it. If I understand it and can use it, then I will never forget it. right? Which is true. But, you know, sometimes if you're not a mathematics student, you're just trying to get through this course, right? I understand. You just need to know this until finals week, and then you can do whatever you want with the knowledge, right? Keep it for as long as you want, or just dump it all, right? So, so how can you memorize this, you know, short term if you're still having trouble like wrapping your head around the construction of these graphs? Just make some flashcards, you know, like put on one side, like on what, I don't have any flashcard, I got a little sticky note, but for example, you could put like f of x equals x squared, and then on the back side of the flashcard just have a little graph drawn and put the appropriate base graph. And you could study these with yourself, you know, doing flashcards. I don't know how you would do this with someone else. You'd have to, because how do you describe like some of these shapes? This is kind of something you'd have to do on your own. You'd read the flashcard and then picture it in your head and then flip it over to make sure you're right. And you know, that's a legitimate form of studying. In fact, I even do it. I'll show you all the way I do it, just because I have done it in the past to memorize some stuff before like a analysis exam. But this is how I do mine, which looks absolutely terrifying, I know. But you can do this and build. You could write these by hand to build little question flashcard. Like this is the front of the flashcard and it lines up with the answer on the back. And that's kind of a way, if you don't have flashcards and you want all of them on one page, you could do something like that. And I found that that is helpful for memorizing stuff. Okay, but I don't want to go into too much detail about telling you how to study because you probably know what's best for you. All right. So transformations now. So officially 2.6, we're moving into transforming these functions. So in Wednesday's lecture, I pointed out that something like if you've got a base function and you add or subtract to the outside of it, that essentially results in a vertical shift. You're adding to the outside of the function, that's a vertical shift up. And if you're subtracting to the outside of the function, that's a vertical shift down, which sure, that makes sense. So real quick, like something like if I have a function like f of x equals x squared plus 3, then I would expect that to be that base graph of x squared, scooted up by 3. So I know x squared is like a parabolic shape. Scooted up by 3 and just plop the parabola right there. And I pointed out in Wednesday's lecture that it's sometimes really helpful to note where the origin of the graph is moving, like literally where the point that was at the origin. The original parabola is down here at 0, 0, right? Like that's the origin of it. Whoops, that's the origin of it. And if I'm adding 3 to the y value, scooting up means adding to the y value, then that new coordinate point where it starts would be 0, 3. That can be really useful to write down before you draw the graph. I'll give you another example. Actually, before I give you another example, let me say the other class of transformations that I talked about in Wednesday's lecture is that if you add or subtract inside of a function, then that results in a horizontal shift left or right. And things are a little bit backwards here. This, when you add inside, it's a horizontal shift left, like into the negatives, which is counterintuitive, I know, but that's how it works here. And for f of x minus c, that's a horizontal shift right. I know I'm going fast, but remember, if you missed Wednesday's lecture, then after this, you can go back and see all this stuff in much more detail. So if I said f of x, I'm just going to pick a parabola again because they're a familiar shape. Let's say x plus 3 all squared minus 2. Okay, so what am I doing? I'm adding 3 inside the function. So the base function is x squared. Take all these extra operations away, it's just an x squared graph. Base graph is x squared. I'm adding 3 inside. That's going to result in a shift to the left by 3. And I'm subtracting 2 outside the function. That's going to result in a downward movement, of vertical shift down by 2. So where does that put the, where does that put this shape? Well, again, it can be helpful to note where did that origin point go. So let me write that down. So the original origin point of the graph right there is at 0, 0. That's what we call the vertex of the parabola. But it's just a nice point to note. And that point is going left by 3. So I'm going left by 3. So the new x value will be -3. Left by 3. So that scoots it left into the negatives by 3, and also down by 2. And it's still going to maintain that same shape that it had as a base graph, which is the parabola shape. It's just now that point that I'm noting to help me graph it is all the way down here at -3, -2. And then I'm going to draw it. I'm not going to be super concerned with how good my drawing is here. The point is that it should be a parabola just starting at this point down here in the third quadrant. Oops, there we go. Okay, in Wednesday's lecture, this is pretty much as far as I got, though at the end I went on a rant about domain and ranges. That's important. You should go review that, though I'm not going to be, typically in this class I am a bit more concerned with domain and range issues, but I'm not going to prioritize them as much, so I'm not going to redo them here, but it is important that you see that. So you should check that out as well. Also, I did do another example with a different type of graph, shifting it around. I think I did a square root graph, if I'm remembering right. And now what I'd like to do is do a rational function, or rather a reciprocal function. One of the 1/x ones, and I'm going to show you what that looks like when you scoot it around, because that gets a little bit weird because of the shape of those graphs. So still just talking about moving graphs left, up, down, left, right. Let's consider, or let's graph f of x equals 1/, let's say x minus 2 all squared plus 3. All right, what is the appropriate way to go about doing this? Because this might get a little hairy here. I'm going to put this overlapped there. There we go. So the base graph, the base function is 1/x squared, right? 1/x squared. If I take the -2 operation away and the +3, all this extra stuff attached, it's just a 1/x squared. So I have to know, the knowledge I have to bring to this problem before I even really start it is to know that the base graph for this function is going to look like this. There, like this. Did my camera move? Hang on. I don't think it's vertically centered anymore. That's a bit better. Okay. So maybe I can even write it down. I can say base graph it's like that. Okay. All right, and I see what I need to do. I need to scoot this thing left or not left, I'm sorry. I need to scoot it right by 2 because I'm subtracting inside next to the x. I'm subtracting inside. That -2 there is going to correspond to a right shift by 2. And how far up do I need to shift it? Kimberly, how far up should I shift this graph?
3 points.
Yes, thank you. And up by 3. So the problem now is it's not really like interpreting this stuff, right? I feel like we could all get this statement down. We understand this as long as we understand these rules, as I've written them back here, these rules and these rules, which again, I go into much more detail in the last video. So this part's not really the issue. It's how the heck do we do that with this graph? So the other graphs have these points, these special points that we can anchor ourselves with, like the point there in the parabola. That point there, as long as we can figure out where that point is moving, then we can pretty much just draw the rest of the parabola because we know the shape of it. There is no such, but this graph does not go through the origin. It doesn't have any like nice stationary points, right? I mean, it does, but like they're harder to note. So instead, we think about where their asymptotes are moving. So what we have to note is this base graph. Base graph has asymptotes, and asymptotes, if you don't remember, are those they're like lines on the graph, understood lines on the graph that the graph of the function will never cross. It approaches, it gets very close, but it never crosses them. So this thing has asymptotes. It has vertical asymptote where on the y-axis, right? And how do I write down the y-axis like algebraically? That, well, it's x equals 0. That's the y-axis. When x is equal to 0, that's right down the middle. And horizontal asymptote at the y-axis, no, sorry, I just said that. At the x-axis, right? The x-axis, it has a horizontal asymptote. And how do I write down the x-axis algebraically? Well, that's at y equals 0. Okay, so I've noted where these asymptotes are. And just to draw them on your base graph, here is the x equals 0 vertical asymptote. That's at x equals 0. And the horizontal asymptote at y equals 0. And yes, I do mean x equals 0 and y equals 0 here, because remember the way you notate a vertical line on a graph is by x equals some number. And specifically here, if I want specifically the whole y-axis, that's going to be where x is equal to 0. Everywhere along the y-axis, x is equal to 0. And vice versa, on the x-axis, y is equal to 0. Okay, so why do I like algebraically notate these? Well, because now I'm going to talk about shifting the asymptotes of this graph. That's what's going to help me anchor. These are going to be like my anchor points, but they're not points, right? They're whole lines. These are going to be my anchor lines, and that's how I'm going to do these shifts. So what I'm going to do when I say I need to shift this graph right by 2, I'm going to shift if I'm shifting right by 2, I'm going to shift its vertical asymptote, right by 2. And x equals 0 is its vertical asymptote. What would its new vertical asymptote be at if I'm shifting it right by 2? What do you think, Nikita? What would the new vertical asymptote be? It's at x equals 0, but I'm going to go 2 positions to the right. What number would you expect for x to be equal to represent that new vertical asymptote? How about Aviana? What do you think?
Would it be -2?
But I'm shifting to the right, though. So +2. So when I say shifting to the right, that means into the positive. So keeping in mind that to the right means over here, to the right means positive. Now I know that you're seeing -2 in here, but recall that when you're working inside the function, things are a little backwards. So when you're subtracting 2, you're actually like scooting it that way to the right into the positives, which is counterintuitive, I know, but shifting the function right by 2, in this case, its vertical asymptote is going to shift right by 2 to x equals 2. And I'm going to shift up by 3 means shift. So if I'm shifting up by 3, I'm going to lift this this horizontal asymptote up by 3. So you see, these get a lot more involved than the shifting these things around is, it can be a bit more involved than the parabolas and root functions. So instead of the horizontal asymptote being at y equals 0, I'm shifting it up by 3. It's going to be at y equals 3. Okay. So where is this new graph going to be? Let me draw the new asymptotes. I'm going to plot down the base graph, and then I'm also going to, let's see. That's fine. Base graph has asymptotes just on each axis. So I'll draw these with the orange line there. It's kind of hard to see them because they're right on the axes. And the base graph was just like this. Okay, now I'm going to, all right, hang on. Okay, I'm going to need to go right by 2 for this vertical asymptote. So that vertical asymptote is going to be there. So vertical, that means my function should now try to hug this line, okay? And then what about the horizontal asymptote? Well, it's up by 3, so 1, 2, 3, that's where my new horizontal asymptote is. So now my function should try to hug this line. All right. So you can almost think about, it's almost as if the axes have like floated over here, and you're going to keep the shape of the graph the same and everything. It's just going to go from here and here to up here. So what do I mean by that? Well, we're going to have this shape for our shifted function. It's going to hug this line, and then same thing on this side over here. And there it is. There it is. So these are this new horizontal asymptote is y equals 3, and this new vertical asymptote is x equals 2. I'm going to show you this on Desmos as well real quick. Where's my... Oops. Okay, let's go to Desmos. And what am I typing in? Let's see. Okay, let's type the 1 over x squared graph. There it is. There's 1 over x squared. And then here is, now let's see, I need to do x minus 2 all squared and then plus 3. Oops, no, plus 3 is outside. Come on, there we go, plus 3. Very important where you add and subtract this stuff. These reciprocal functions can be really weird in their graphs. So I need to be very particular about the way I'm graphing, the way I type it in over here. It has to be exactly the same as what I wrote down in the problem. And if I zoom out a bit, you can see how it's been scooted over and lifted up. So like if I showed you this picture and you could tell me, okay, it's going to scoot right by 2 and up by 3. And then we graphed this blue function as I've drawn it here in Desmos. The transformed one is in blue. You would say, yeah, that's what I was expecting, like right and up. But getting it down on paper can be tricky, and that's why I dug into the asymptotes. That's why I did that. Okay. So now let's go to other types of transformations, which are when we multiply and divide by a number. And actually, we're going to do these in chunks here. Let's just talk about negatives first. Let's talk about multiplying. These are kind of easier. Multiplying by negatives. So say we have a function, base function f of x. What does negative f of x do? So a negative on the outside of the function, on the outside of the base function. What does that do? It flips the graph over the x-axis. Okay. A negative inside the base function flips the graph over the y-axis. All right, examples. Let's get straight into some examples. Let's, I didn't even number the last, yeah. It doesn't matter. I'll just call this example 1 for today. The point is, when you go and study your notes, study all of them, right? Okay, so example 1, let's graph f of x equals negative x squared. So that's this first case where the negative is on the outside of the base function being x squared here. And let's graph g of x equals, so if I want to put the negative inside, it'll look like that. Negative inside, like literally inside the square function. By the way, I'm using, in my general setup up here, for like the rules that I'm writing down, I'm using f of x. That's not this f of x, right? This is just like a super generic function, like representing like x squared or x cubed or square root of x or something. And then I'm using this here as a specific example. So this, if you're trying to line it up with this rule here, for this rule, my f of x is just the x squared thing, and I'm stacking a negative outside of it. I'm just using the same name here because we use f of x to represent like all sorts of functions, right? It's like the go-to notation for a function. All right, so what do we bring to this? We have to know what x squared looks like, and we do. It's a parabola, right? We have to know what the negative does on the outside. Well, here's the rule. It flips the graph over the x-axis. So we have to know how to do that. We have to know what that's going to look like. Well, my base graph, which I'll draw as a dotted line, is this parabola. That's the x squared base graph. But I need to reflect it over the x-axis, or flip it. Reflect is like the more mathematically correct term. I'm just saying flip here because same thing. So when I flip it over the x-axis, we're calling that this is the x-axis. So it's just gonna be a mirror image right down here. There it is. That's it. That's it. Nothing else to say there, really. Now, there's a little bit more to say about its range. Whenever you go watch the video, or if you already have, and you watch the end where I talk about domain and ranges, you'll note that the range of an x squared graph, the values it can output are 0 to infinity, right? The range of this graph, just by the way, the range of this graph would be the opposite, right? 0 all the way down to negative infinity, which we would notate this way, with negative infinity up to 0. That's not part of the question here. I just wanted to note it. Now, what about g of x? So this is f of x over here, the first one, and now let's graph g of x, because it's a different case, right? So of course it's got the same base graph as x squared, right? That's x squared. Let me finish labeling things. So this is the negative x squared graph down here. All right, what happens, Taylor, what do you think is going to happen to this parabola if I reflect it or flip it over the y-axis? And it's kind of a trick question.
You said what would happen to the what?
What would happen to this parabola if I flip it over the y-axis? So here I flipped it over the x-axis, so I took the shape and flipped it over the x-axis, but here I'm trying to flip it over the y-axis. So if I spin this thing around the y-axis, is it gonna look any different?
No, because
right, exactly. That's kind of
the y-axis.
Right. This is the y-axis, right?
Yeah, that's what I'm saying. It's not gonna look any different.
Right. Exactly. Yeah. I said it. I did kind of give you a trick question there. Sorry, but yes, you're right. It wouldn't look any different, and it would just because. And why is that? Like, surely we can say a little bit more about that besides just, oh, it doesn't look different. There's more to say, right? So first of all, let me just say that is the same. There we go. And it's because we stuffed the negative inside the function. And what does a squared function do to negatives when you stuff a negative inside of it? It just absorbs it, right? It says a negative times a negative is a positive. So any function that does this, where it absorbs negatives, when you reflect it over the y-axis, it's not going to do anything. Cool. Let's look at some more examples of things.
Wait, what was that last part? It skipped.
Yes. What's that?
What was the last part? It skipped.
Oh, I said any function that absorbs negatives will not, when you flip it over the y-axis, it will not change. And I'm going to say more about that. I'm actually going to write that down because there's I'm coming to these new definitions. So I'm just alluding to it here. I'm going to give you the official statement after we look at a couple more examples here. Because if you all are thinking well, that kind of seems important. Well, you're right. And, and I'm kind of, I'm building up to it here. So let's do example 2. Let's look at a function. So example 1 was x squared, which is a function that takes in negatives and says, if you give it a negative inside the function, it just outputs a positive again. It doesn't really change. Let's look at a function that we are sure does not do that, which is a cubic function. So let's graph f of x equals, so first we're going to mirror what we did in example 1 with stacking it on the outside first and putting it on the inside. So I'll just kind of mirror how I did example 1. I'll put f of x over here, f of x graph over here. So I've got to know what x cubed looks like. And it's sort of almost like a half parabola on that side, and then the other side points down. So there's my x cubed base graph. That's my x cubed base graph. And now I go look at my rules that say, okay, when I stack a negative outside the base function, just like this first part here, I flip the graph over the x-axis. Okay, so I'm going to help you all out here and show you what happens here. If I flip this over the x-axis, so over the horizontal axis, then this part ends up mirror imaging down here. So that's this right-hand side flipping over the x-axis. So I'm going to take this and I'm going to spin it around the x-axis. This part ends up flipping up here. There's my negative x cubed graph. Okay. Cool. Okay, so nothing crazy there, just understanding how to flip a shape like this over the x-axis. It's mirror image. So I'm taking like this arrow and flipping it down here, and this arrow flipping it up here. All right, now let's graph. Okay, start with my base graph. X cubed again. Okay, now I know that when I stuff a negative inside, that means I should reflect over the y-axis. So Maya, if you flip this over the y-axis, what would you expect? Like, can you describe the shape, like in terms of how it looks compared to this one?
Can you say it again? Because it broke up a little bit.
Yeah, if you take this shape here and you reflect it over the y-axis, so taking this arrow and reflecting it here, and this whole thing and reflecting it over here, how's it going to look as compared to this red line?
Would it look the same?
Yeah, good. Yes, it would. It would. I know. Sometimes when I ask y'all trick questions, it's like I think I know the answer, but that seems too easy. But that's right. They look the same. Okay, so what's happening here? We got an even function that when you reflect it around the x-axis, it reflects over the x-axis, right? It flips upside down. But when you try to reflect it over the y-axis, it does nothing. We've got an odd function that when you do either kind of reflection, it does the same thing. So these are, there's something more to say here, and let's go ahead and say it, which is that, whoops, a function is called even if, I'm going to say it in like colloquial terms first, in colloquial sense, meaning like not technical, if it absorbs negative values. So that's like the parabola shape. If you stuff a negative inside of it, so I'm specifically talking about that case where I'm stuffing a negative inside of it, if it absorbs the negative value, then it's called even. That's exactly what our example 1 part 2 did back here. Stuffed a negative inside and it didn't change the shape, right? It just stayed right where it was. So if it absorbs negative values, it's called even. In particular, like technical math definition, this is even. You stuff a negative inside of it and it doesn't change. It just turns back into the function. So as an example, I'll use that x squared graph we have, or x squared function. So if we have f of x equals x squared, so I stuff a negative inside of it. So f of negative x, so I'm now working with the algebraic definition of the function instead of a picture. So that's going to be plugging negative x into the function, right? If this is the function, plugging a negative x in, making sure that I'm wrapping parentheses around it. But what is negative x times negative x? Well, that's just x squared. And that's just the function. That's just the original definition of the function. So what do I end up with? I end up with stuffing a negative inside of it doesn't change the function. That's called an even function. And it's no coincidence at all that the exponent, the exponent is what makes it even here, right? If it's an even exponent, then it's going to be an even function, right? There are more functions that are even that have nothing to do with exponents, but for our purposes, so I'm going to write this down now. For our purposes, and what I mean by that is for the functions that we're going to look at, x to the n, where n is even, is an even function. So that's like, that makes a whole lot of sense. If it's got an even power, like what I've got here, like a 2 or maybe a 4 or a 6, then it'll be an even function, meaning that if you stuff negatives inside of it, that it doesn't change. Also, What other even functions do we have? 1 over x to the n, where n is even. So that 1 over x squared, 1 over x to the 4th, is an even function. Now, I can't extend this to the root functions because I can't stuff negatives into a root function to begin with if it's even, so they just don't, they don't obey this rule. But the the power functions, x to the n, like where n is even, and 1 over x to the n, where n is even, those are both, oh, I left out the word even here, I'm sorry. I'm like thinking and talking and writing, so there we go. 1 over x to the n, where n is even, is also an even function. And let's see if that makes sense. If we go back and look at an even function, 1 over x squared, I'll give you a second to write this and then I'm going to cover it up. Okay, 1 over x squared, here it is. If I reflect this over the y-axis, it doesn't change, right? If I flip this side over here and this side over here, it doesn't change. Cool. Maybe I should write that down, like the graphical representation here of this rule. There's a lot to say about this rule. So algebraically, a function is called even if it absorbs negative values. Here's a quick example of that. For our class, we're going to call even functions basically the power functions and reciprocal functions that have even exponents. And as a graph, for the graph, like how do I translate this rule to graphical, you know, like a graphical representation? A function is even if flipping it or reflecting it over the y-axis has no effect. Cool. Now, what about the odd functions, right? Because I did an example 2 with f of x equals negative x cubed and all that. So let's look at that. Let's consider this now. All right, so we all good so far? I'm not moving too fast with the notes or anything. Okay. So what about this case? So the last case we saw before we really started writing down the definition that what was happening is reflecting over the y-axis did nothing to the function for an even function. And here, that's not the case, right? It's that reflecting over each axis just results in the same thing. So reflecting over the x-axis is the same as reflecting over the y-axis. That should be what we should expect from this next definition for odd functions. And let's walk through that now. So a function is called odd. Is called odd if what? Not if it absorbs negatives, but if it takes negatives and puts them outside the function. All right, what does that mean? Well, algebraically, that means if you try to give it a negative inside the function, then it just like spits it out on the outside, just like that. So it doesn't absorb it. It doesn't like just take it in like an even function and just like give you nothing. It takes the negative in and spits it out on the outside of the function. So do a quick example. I'll do a quick example. So let's let f of x equal, what's a classic odd function? Well, x cubed, that's fine. So I'm going to give it a negative, stuff a negative inside the function, so literally like inside parentheses. Then I'm going to cube it, but negative x cubed is negative x times negative x times negative x. There's an odd number of negatives, so I should expect those negatives to maintain, right? There's still going to be one. In other words, I end up with negative of x cubed. But the original function is x cubed, so now I've negated it. It spit the negative out on the outside. So when you have this sort of relationship, the function is called odd. That's an algebraic representation of it right here. What about a graphical representation? Hold on. Oh, let me go in the same order I'm doing the, so I'm trying to model how I did the definition of even. So let me keep that going. So before I talk about the graphical relationship, I'll say for our purposes, so I'm going to point out which functions we're going to see that are odd. X to the n and 1 over x to the n. And now we can talk about the root functions where n is odd are all odd functions. So like, you know, x cubed, or maybe 1 over x cubed, or maybe just 1 over x, right? Because 1 over x, in that case, n would technically be just 1, which is odd. Or maybe like a cube root of x. Those are all going to be odd functions because n will be odd. So that kind of lines up with the rule I said for even functions, where I said x to the n and 1 over x to the n are even if n is even. But note that in the even function part, I left out the root functions because, and why? Because this rule is all about, or these rules are all about stuffing negatives into functions. You cannot stuff negatives into an even root function, like a square root, right? So that's why, in particular, the root functions are left out of the discussion of, you know, being even or not. And okay, finally, the graphical representation. If a function is, or I'll say it this way, a function is odd if, so it's not quite the same, you know, it's not quite like exactly opposite to even, right? But a function is odd if flipping over the x-axis is the same as flipping over the y-axis. Okay. There's so much to say about graphing functions. I mean, we could literally do like an entire course, I feel like, on graphing functions and transforming functions. And there's just so many different avenues we can go. But and in fact, we still have like a whole chunk of transformations left to talk about, which is vertical stretching and horizontal stretching and compression. But for now, since we've talked about negatives, how negatives affect a graph, and also this definition of even or odd, let's do one more two-part example with flipping graphs, and then let's do an example of deciding if some random function is even or odd. And let's try and get through it quick because we only got 10 minutes. So. I might go through this too fast for you, but you know, you can always go back and review it later. So graph each function. Let's call this officially part A. F of x equals -1 over x squared, and g of x equals cube root of -x. Okay, let me draw my two graphs. So just a little bit more practice, literally just drawing these reflected graphs. Okay, 1 over x squared, got to remember that's that shape with the two like L-shaped things both pointing up, but a negative outside the function reflects it over the x-axis. So this negative is outside of the base function of 1 over x squared. It's not stuffed in there next to the x. Right? So I should expect this graph to rotate over the x-axis right down here. Now you can only imagine how complicated this stuff gets when you start putting together shifts, up, down, left, right, and reflections, right? So we will do some of those next time, I guess on Monday. All right, but that's it. That's it for part A here. Just flipping the graph over. Now, over here, I've got a cube root of x, which I know, I'll write it down just in case, you've forgotten, but it's like that. Like that kind of shape. That's the base cube root of x graph. But I want to stuff a negative under it, which results in a flip over the y-axis. So I'll take this graph and I'll take this leg of it and I'll flip it over the y-axis. So I expect it to be over here. And I'll flip the other part over the y-axis, which I'll put it over here. There it is. There's that graph. And by the way, this is an odd function, so I could argue that this is the same as just flipping it over the x-axis. Do I need to point that out in order to solve this problem? No. All I have to say is, okay, negative literally inside the function. That means flip over the y-axis. So that's what I'm going to do to the function. I'm going to take its base graph and flip it over. Flip it over the y-axis. Okay. Okay, any questions about that one? I went through that one even faster than I meant to. So we all good there? Okay. Okay, example 4, right, I think. Now we're changing gears here. We're just going to be practicing using the definition of even and odd, not graphing functions. So decide these are kind of some classic problems coming, whether each function is odd, even, or neither, right? Because they can be neither. Let's say part A is f of x equals x to the 4th plus x squared. B is g of x equals x cubed plus x squared. And C, h of x equals x cubed plus x. Okay. How do we do this? We stuff a negative inside the function and see what happens, basically. Now notice f of x is built from two even parts, right? An x to the 4th and an x squared. Let's see what happens for part A. Stuff a negative inside, just like this, into both parts. All the x's, stuffing a negative inside. But the negative gets absorbed by the powers of 4, right? And powers of 2. It's even exponents, so they just end up staying exactly the same. But that's just exactly equal to the original function. So we end up with this relationship. So it's even. And that kind of like makes intuitive sense. If the pieces building it are all even, then you should expect the result to be even. Part B says g of x is x cubed plus x squared. So I'll stuff a negative inside the function. So just rewriting it with these negatives. Now what's going to happen here? Well, x cubed does not just completely absorb it. It spits it on the outside like this, right? That's what an odd exponent does. But the x squared function does absorb it. So it just stays positive. Is this equal to g of x originally? No, because it has an extra negative. Is it equal to, is it odd? Is it equal to just putting a negative on the outside of g? Well, no, because only one of the signs changed. So this is neither. This is neither. And to really point that out, like that difference, let's look at this one where the h of x function, where both of the pieces are odd. What do we expect to happen here? Well, negative x cubed, that spits the negative on the outside because it's got an odd exponent. And then we have plus negative x, which I can just leave as like that, or I could write minus x too, right? That's fine. But this is exactly equal to pulling a negative outside of the original function, because they both, all the signs changed, right? Both of the signs changed. But that's just the same as pulling a negative all the way outside the function. And this relationship is called odd. So what's the bottom line here? What's the bottom line? If all of the pieces that build the function are even, then you should expect the whole function to be even. If all of the pieces that build the function have odd exponents, so like in this case, a 3, and technically this is a 1, right? Technically, remember that? Then you should expect the end result to be odd. If there's a mix of odd and even, then your function will be neither. Most functions in general are going to be neither odd nor even, right? Neither odd nor even. Now, are there functions outside of this class, like outside of just polynomials dealing with even and odd exponents or reciprocal functions and root functions? Yes. If you have to take trigonometry, you'll learn about some sine and cosine functions, and those have these properties as well. But that's not what this class is about. So, okay. That's where I'm going to end it today. We still have stuff to talk about in 2.6. It's a pretty huge section, so we will continue that on Monday. You guys are good to go. Stick around if you have questions.